Energy stored in a magnetic field. Now if we go back to our first case in the RL circuit when S1 was closed and S2 was at position A, so this RL was connected to the battery, we found this equation from Kirchhoff voltage law for this loop. And if I rewrite that equation here, it is epsilon minus IR minus L di dt is equal to 0. Now I take this equation and multiply it by current. So multiply by I will obtain I times epsilon, that's the power provided by the battery, is equal to I square R, the power dissipated by the resistor, plus Li di dt, that would be the power dissipated by the inductor. So this is the power delivered by the battery. This is the power on the resistor, and this will be the power on the inductor. So we can see this, if you can see that from this power equation, power on the inductor is Li di dt, and this is the rate of change of potential energy, du dt. Therefore, we see that the potential energy stored in the inductor is the integral, because the dt's, I don't need the time derivative here. If you get rid of these dt's, it will be integral from 0 to I, L I prime di prime. Okay, so if I look at the change in the potential energy from zero current to current I, it's basically the integral Li prime di prime. Okay, so this gives me the potential energy U 1 over 2 Li squared. So that's the potential energy stored in the inductor when it carries a current I. And this is basically similar to the potential energy stored in a capacitor when it stores a charge, 1/2 C delta V capacitor square, or Q squared over 2C. Now, the inductance of a solenoid, we can recall, the inductance of a solenoid we have found to be L equals mu 0 A n squared divided by L, which is mu 0 A L divided by L squared multiplied by n squared. So this is basically mu 0 n squared multiplied by V. So n is the number of turns per unit length, and V is the volume, which is the area A multiplied by the length L. And the magnetic field inside the inductor is inside the solenoid is mu 0, number of turns per unit length multiplied with current. So the energy stored, potential energy stored, will be 1 over 2 Li squared, which is 1 over 2 mu 0 n squared V, that's the inductance. And for the current, I can substitute B divided by mu 0 n, so it's going to be B squared divided by mu 0 squared n squared. Now you can see that this mu 0 will get rid of this square, and n squares will cancel, and therefore I will be left with b squared divided by 2 mu 0 multiplied by the volume V. So basically I can define an energy density lowercase u sub b as b squared divided by 2 mu 0. So when the solenoid has a magnetic field B, it's going to be storing a potential energy per volume b squared divided by 2 mu 0. And this is similar to the potential energy stored per volume in an electric field, which is 1 over 2 epsilon 0 permittivity of free space E squared, the electric field square. So we can see that this potential energy density in a magnetic field B squared divided by 2 mu 0 is valid for any region of space where a magnetic field exists. Now we can check this result by looking at the second part of our analysis, the second KVL. This is our KVL2, where we found the current to be epsilon over r e to the minus t over tau. So for KVL2, the current as a function of time is epsilon divided by r e to the minus t over tau, where tau is our time constant, which is L over R. Now, if I look at the power dissipated by the resistor, which is I square R, it is equal to the integral from time t equals 0 to infinity, I square R dt, and it is integral from 0 to infinity epsilon square over r square r e to the minus 2t over tau dt, and this will give me epsilon square over r. The integral will give me minus tau over 2 e to the minus 2t over tau evaluated between 0 and infinity. So this will be equal to epsilon square over r multiplied by L over 2r and this will give me epsilon square over r square, which is the current. So this will be 1 over 2 L I square. So basically this will be the energy stored in the inductor when it carries a current I. So we can see that the potential energy stored in an inductor when it has a current I is basically 1 over 2 Li squared, which is the previous result I have obtained here. So when the current is equal to epsilon over R, so I obtain 1 over 2 Li squared. So this, remember, is the steady state current in the first case. It was epsilon over R. So that steady state current I denote by capital I is 1 over 2 Li squared. So this was the energy stored in the inductor, which gets dissipated in the resistor as I square R. And you can see that there's a transformation. This energy is basically taken from one circuit element to another circuit element and dissipated in the resistor. So for the energy stored in a magnetic field, if you look at our RL circuit, the first Kirchhoff voltage law basically tells us that following this loop, IR plus L di dt minus epsilon is equal to 0. The current basically follows the voltage drop. And from this equation, if I multiply this equation by I times epsilon, I times V is the power. So this is power provided by the battery is I square R, the power delivered to the resistor, plus Li di dt, which is the power delivered to the inductor. And the power delivered to the inductor is the rate of change of its potential energy, du dt. So if I look at the potential energy as a function of time, basically I can integrate, if I multiply both sides by dt and integrate, the dt's will cancel here. So I integrate this from 0 to I obtain Li di dt. So basically I have multiplied this equation by dt both sides and dt is cancelled, and this way I can integrate it from time t equals 0 to from 0 current to current I. So you can see that Li prime di prime integral gives me 1 over 2 Li square from 0 to I. So the potential energy stored in an inductor when it carries a current I is 1 over 2 Li squared, which is similar to Q squared over 2C or 1/2 C delta Vc squared for the capacitor case. Now I recall the inductance of a solenoid, which is mu0 times cross-sectional area A, number of turns squared divided by the length, which is mu0 n squared, number of turns per unit length squared, multiplied by the volume. The magnetic field of a solenoid inside is uniform, and it's approximately uniform. It's mu0 times permeability of free space times a number of turns per unit length times current, mu0 ni. The energy stored is 1/2 Li squared, so it is 1/2 L mu0 n squared V I squared B squared over mu0 squared n squared, which is B squared over 2 mu0 times volume V. So the energy density, energy per volume is B squared over 2 mu0, which is similar to 1/2 epsilon 0 E squared in the case of electric field. So in a magnetic field B, we have energy density B squared over 2 mu0, but in an electric field E, we have energy density 1/2 epsilon 0 E squared. If we follow the second part of our RL circuit analysis, where the current drops from epsilon over R to 0, there is power dissipated by the resistor, which is du dt is equal to I square R. And we find that by substituting this current here, we obtain, so this is actually a drop in potential energy. So normally this should be coming with a minus sign, and that minus sign will basically, if we do this properly, make this a plus. So this is going to give us, by substituting this solution into the power expression, a power dissipated as epsilon square over R times L over 2R. Well, this actually is going to give a minus sign, evaluate that infinity is 0, so I take it back. This du dt is equal to I square R. So let's get rid of this minus sign here. So we do obtain a decrease in energy as time goes by. So this is going to give us epsilon square over R times L over 2R, which is 1/2 Li squared. Now, what is 1/2 Li squared? It was the original energy stored in the inductor. Why? Because the steady state current was epsilon over R. So that's this I here, epsilon over R. So the energy stored in the inductor was 1/2 Li squared, which is now transformed into energy dissipated in the resistor I square R.